Hello everyone, my name is Katerina Galitskaya and this is the fifth tutorial in the 6 episode series on antenna simulations in Nullspace. So far we've been working with antennas in free space from a single bow tie element to an array with beamforming and radome integration. But the real challenge begins when we move from an isolated setup in free space to a real installation environment on a telecom tower. In this tutorial, we'll model, simulate, and post-process an electrically large problem for element antenna array mounted on a 10-meter telecom tower. You'll see how the presence of the tower affects the radiation pattern and why installed performance can differ so much from a free space one. So let's get started. So we start with radome, with our radome integrated antenna, and you can see that I imported the like tower step model as well here, and this is the step model of some random telecom tower, 10 meters long. You can see that the size comparison of our antenna and tower is significant. So the difference is significant. So this counts as electrically large problem because our antenna works at 1 gigahertz and mast is 10 meters long. So this will be very interesting to simulate. One problem that need to be that you need to be cautious about is when you work with this imported step models or some other like 3D formats. The models that come imported, they can be not maybe always kind of good quality. There might be some like small features that you don't want in your simulation, maybe some surfaces that is not meshing so good. So in this case, it's there is a good feature here that's called the mesh quality in Nullspace. So we can see how our mesh, how our model is meshed, and we can kind of work with that. We can see if we need to maybe improve our mesh. So here you have a scale, and then you can see how it mesh the whole model, right? So what I've done in the beginning is that I imported the model and then I checked the mesh quality after I meshed the model initially, and found some like maybe problematic areas. For example, I had some like screws here that really I didn't need because they don't affect my antenna performance. So I manually removed them, and now I have quite a good mesh quality, as you can see. So I'm happy with that, and I can move further with my simulation. So this is something that you need to be cautious about, that sometimes imported step models or some other 3D CAD models, they require some additional work. If we move now to the simulation setup, in the simulation setup, it looks very similar to what we've done before. The only different line here is that we use compress solver now. So finally, we moved now to really electrical large model. Before we worked with the antenna array in free space. So now we moved to electrical large model and we can use compress solver. So compress solver is still full wave solver. So one good thing about Nullspace is that it solves everything in a full wave solver, right? In other software with this kind of electrical large problem, what you usually see is that it uses asymptotic approach, such as like shooting bouncing range, for example, or something similar. I mean, it's good for some simulations, first approximation and so, but always, of course, we want to have a full wave simulator, but it takes a lot of time usually to simulate, especially these kind of huge problems with full wave simulator, and also a lot of memory, right? So these compressed solvers help with that. And for example, I run this model on my laptop, just like some regular laptop, and I was fine with the memory usage, and it took like several hours to simulate, so it was quite possible. And just to think about that, this is actually full wave simulation of an antenna array placed on 10-meter long telecom tower. For me, it's very really incredible that I can do that on my like a regular laptop. So other than that, we have all our like normal simulation setup. We have some far field simulations and so on. So if we move to post processing, we get our S parameters, active S parameters. We get our gain, and we get our cuts. So everything usual. What I done here, one thing is I think very important is to compare our free space antenna simulation with our installed antenna simulation. So I imported the data from our previous simulations with the free space antenna simulation. So I imported gain versus frequency, azimuth cut, and elevation cut. So we will look at that. So then I plot them, and in the end, as well, it's always interesting to look at 3D radiation patterns. So this is what I plot here. Let's look at results. What we see here is that active parameters are quite similar to what we had before. Uh, Resonant frequency is there. Uh, Levels are a bit lower, so worse matching. So that is something that we need to keep in mind, because the more details you add into your simulation, the more you need to be cautious about, like if you need to maybe fine tune your antenna more, or like add some matching elements to that. But other than that, the behaviors and the like resonant frequency is the same in this active S parameter, so that's good. Then if we look at our gain versus frequency. So we can see here that our installed gain has some strange ripples out of sudden going on, and behavior is changed from what it was before, right, with this dashed line. So this, of course, we can expect with the installed antenna, because we have this huge metal thing that's kind of right behind our antenna, and of course a lot of reflection can happen there, and some of this reflection can come back to antenna. So we need to be, that's why we do the simulation, that we need to be cautious about that. This is how it will be in real life. Our antenna, that is, we kind of like so tuned and matched, and so in free space it will not be the same when it's like actually installed on something. Then if we will see our 3D radiation pattern, we see that there is some ripples go out of sudden with the on especially on azimuth, and we can see it as well here. So if we plot azimuth here, so all the dashed lines are what we had before in the free space, and solid lines is installed antenna pattern, and you can see that there is some ripples, and of course we want as smooth azimuth as possible. So this is also something that we need to keep in mind. And if we talk about elevation, so the biggest difference is on the back radiation. And back radiation, it's also important. We have this parameter as front to back ratio, for example, right? So we need to be cautious about that, and we need to know that with our installed performance, the antenna have different changes behaviors with especially with the back radiation, and you can see that side lobe level, for example, is higher here. So this is something I think very great, that we can simulate such a such close case to real life, and also in the full wave simulator. So we are like sure about the accuracy of that. and we can like fine tune our antenna, and maybe that requires less prototype round, less tuning in the lab in the end, right? So in the next episode, we will add one more antenna to that setup. We will see how they couple to each other, how they affect each other. Because usually on one mast we have a lot of antennas. We don't only have one antenna, right? So that will be very interesting, and that will add one more step to kind of reality of the problem. That was all for today. Thank you very much for being with me. Bye bye.